This video is part of the Discrete Math Review for Foundations of Computer Science. This module is on functions. I think it's very likely that you have seen functions before in some capacity, in some math class, at some point, and hopefully a lot of what you know about them already will still apply and we can draw on that experience. But you may not have seen this exact form of the definition before. It's very general and allows us to work with discrete systems as well as continuous systems. We're going to think of a function as a special type of relation. So we start by saying let f be a relation on this Cartesian product S1 through Sn of arbitrary length, where the number of sets is n. And remember, if you've seen functions previously, you probably are familiar with a kind of a rule that they have to follow, which is that every input gets mapped to exactly one output. So this is the identity function here. And what we're not allowed to do, we would write this as a directed graph, is say, okay, some input goes to some output here. What we're not allowed to do is go to multiple outputs at the same time. And that's kind of the fundamental property we're going to continue to preserve. This would be a relation, and we're going to make a function as a special kind of relation in which we just disallow multiple outputs. So that I think is pretty straightforward, but one thing we need is a way of distinguishing between input and output, because remember, with relations there is no such distinction. We have just a lot of things that are connected to each other, and we end up with some tuple S1, S2, S3, right? It's not clear which ones of these is the input and which one is the output, so we need to figure that out. And we also need to be able to take as inputs to your function tuples of arbitrary length, right? So they should just be restricting your input to one thing, or even if it is one thing like an x, that x should be able to be a sort of complicated object that maybe is actually some tuple like this. All right, so how do we get all of that formally into our definition? So we say f is a function. It's a relation, we already said that, but f is a function if and only if for every n minus 1 tuple, x1 up through x of n minus 1 in the Cartesian product of s1 up to s of n minus 1, that's just an obvious thing you have to do to get that tuple, there is at most one x sub n in that last set, s sub n, the one that we cut out, right? Such that f of x1 through xn, right? And that last thing, such that, means this holds, this relation is true. This is the same notation that we use for relations. All right, so what have we done and what's happened here? Well, notice that in this first tuple, we left out x sub n. And we said that for every tuple that includes everything up to x minus 1, or x sub n minus 1, excuse me, then there's at most x sub n. So what we're doing here is making this separation between the last element of this tuple and everything that comes before it. And the reason we're doing that is to give us this notion of what's an input and what's an output. In this case, everything up to and including x sub n minus 1 is the input, and you want to think of the x sub n as the output. And now we can rewrite this in a notation that I think is a little more familiar and that highlights this distinction, right? And here it is. For a function f, we write x sub n is equal to f of x sub 1 up to x sub n minus 1. So this, like I was saying earlier, is just the input. And in this case, the input is just some arbitrary tuple of things, and x sub n is the output. All right, so now let's just define some things that I think you're used to seeing with functions that we're still going to use here. We have domain and range. And the domain is just everything that our function can take as input, and the way we write that is this tuple x1 up through xn minus 1. From our Cartesian product, cutting off the last set. And it's all of the input that gives us exactly one x sub n in that last set that will be the output of the function. And then finally, the range is just the set of all of the output such that there exists some input that is related to it, or that reaches it, or produces it. So as I said, I think probably at this point in your mathematical career, you have a pretty good sense of what domain and range mean. And if there is a challenge here for you, it is probably just adapting to a new notational convention. On that note, let's look at a few examples of functions, mostly to give you a sense of how you might write a function or different ways of writing one depending on what they are. So first, we can think of a function as a special kind of relation, which means we could write it as a set, since a relation is a set. And if it's a small function, we can write it with explicit set notation if it has a finite number of pairs in it. And then this just looks like a relation, except you would have to check and make sure it really is a function, that each input goes to only one output. You can also write one as a set comprehension. Again, this is sort of extending the idea that a function is a relation and a relation is a type of set. So this would just be some set of tuples, and here it might be infinite. And in this case, you can give a rule that relates these tuples and explains when a tuple is in this set and when it is not. Now, if you do happen to already know the rule that relates the input to the output, you can, of course, still use functional notation, which is probably the way of writing functions that you're most familiar with or have used before. And in this case, of course, the part of your tuple that represents the input is written as the x, and the output is implied by the rule. And finally, you may have seen this arrow notation, which is convenient for representing the domain and the codomain, and the rule is given as a mapping. This is kind of useful for highlighting the idea that a function is moving from one set to another and creating some mapping between them. So hopefully that is enough notation to get you started. Another thing that's useful when discussing functions or analyzing them is to have some vocabulary that allows you to characterize their properties. So I'm going to run through a few terms that characterize properties of functions, starting with total and partial functions. This definition is relatively straightforward. A function is total if its domain covers all of the possible tuples in the product over which it is defined. And if not, it's partial. So this is easy to see if you illustrate it with a small function here. On the left, you can see this is the possible domain, and in this case we have mapped everything to something on the right. There are some collisions, but we don't worry about that. Not everything is covered on the right side, but the right side is kind of irrelevant here. All we care about is that everything, all of our possible inputs, got assigned to something. That makes it a total function. If some of the inputs were not assigned to something, in this case 1, 1 is not assigned, it's a partial function, even if we just miss 1. And it doesn't matter, again, what happens on the right, whether or not we've covered everything. That is related to other properties we will discuss very soon. One tiny point I maybe should emphasize, though, is that even though we mostly don't care about what's going on the right side, if we were to map one of our functions or one of our elements to two things on the right side, that would be a problem, right? In that case, it wouldn't exactly change whether it's total or partial, but it would make it no longer a function. So a next very important property is injectivity, or injective or one-to-one functions, but I like to think of these as functions that avoid collisions. Remember from this previous slide, we did have some collisions here. We said not to worry about them. Now we're going to worry about them. So we say f is injective or one-to-one if and only if it has this property where, remember, this represents the input. If one input is not equal to another input, if we have two distinct inputs, then it is also the case that the outputs cannot be equal to each other. And if you think about that, that is just a definition that says we are not allowed to map two different things to the same thing. And so in other words, we have no collision. So on the left here, I have this diagram showing an injective function. It is not a total function in this case, but it is injective because every arrow, every mapping here hits a unique element on the right. In contrast, here is a function that is not injective, and you can see easily why. We have two elements on the set in the left that are both mapped to 1 and two elements that are both mapped to 2. So there's collisions here, and so this is not injective. And it violates this definition of our inputs are not equal here, but we have equal outputs. So therefore, it cannot be injective. Next, a complementary property is surjectivity, and I think of this as the property of covering everything that you can cover. So we say f is surjective. It's also called onto, if and only if its range is all of the set S of n, all of your possible outputs. Another way of stating this definition, if you're just thinking of two sets, is that f from S1 to S2 is surjective if and only if for all y in S2, there is an x in S1 such that f of x gives you that y. So in other words, we can always find an input that gives us an output for every possible output. This is kind of the same thing. So here's another illustration here. In this case, we have a surjective function because everything in our output set has something mapped to it. And here it's not injective, so we're ignoring collisions. We don't care about that. But it is surjective because everything got at least one, there is at least one input we can find that gives us that value or reaches it. Again, in contrast, this function is not surjective, and the reason is we have this one element here that has nothing mapping to it. All right, finally, bijective functions. Well, this is simple because we've now defined injective and surjective. Bijective is just both things at the same time. And so this is sometimes called one-to-one and onto. Sometimes it's called a one-to-one correspondence. We'll typically say bijective or one-to-one and onto in this class. And the definition is just that it is both injective and surjective. And so here is an example of a bijective function. We are mapping everything in the output once, exactly. And it also happens to be a total function. All right, those are all of the properties of functions that we will cover in this review. We will wrap up now with a brief discussion of composition of functions. Remember, functions are relations, so anything that we talked about, all the operations that you could perform on relations, you can apply also to functions. We will not cover them in as much detail, but I do want to highlight function composition because it's especially useful and therefore also common. But the definition is very, very similar to what you saw with relations already. The first thing we need to do when defining the composition of f and g is to come up with some names for the sets that f and g map from and to. So we'll start with g, and we say g is some function from the set S1 to the S2, and then we say f is a function from some set S3 to S4, and then we assume that S3 and S2 have some kind of overlap, and we express that as their intersection. We call that S. That's the set that sort of bridges between the two functions, as we saw when we looked at compositions of relations. And then again, we define the composition of these two functions, f and g, as a new function that goes from S1 to S4. And we write this as f circle g of x, or f of g of x. Now, as we've said, since functions are just a special type of relation, you've really already seen the definition of composition that we're using here. We're adding a little bit by way of notation so we can have some input represented, or we're using this sort of f of g, this sort of nested notation, which is a little more common for functions, but other than that, really not much has changed. Likewise, when we draw it out in terms of our diagram, this looks very similar. The only difference here is that our arrows, as we go from left to right, they can only map to a single element, right? So you are not allowed to draw from one element out to multiple elements as we could with a relation. Other than that, we get the same thing, and we end up with this mapping that goes from S1 all the way to S4 via S in the middle, which is the intersection of S2 and S3. One difference is we might decide that we're going to write these this function in a kind of the functional notation, the rule-based notation, and so we could have express our composition this way also, where we say now f of x, I give a rule for it, it's x mod 3 plus 1, and if g of x takes x1 and x2 and adds them together, right? Now I have these two functions. If I compose them, I'm going to take two inputs, x1 and x2. I'm going to have to add them together and then mod 3 and then plus 1. And you see that if we take 2 and 1 here and we add them together, we get 3. All right, so that's the correct mapping there. It gives us 3. And then 3 mod 3 is 0 plus 1. That's how we're getting out there. So this time I've just expressed this using these rules to show you how you could also sort of nest rules inside each other. I expect that you probably have done this before, but just in case, I want you to see it as an alternative. Okay, so that concludes our material on functions and also the entirety of our discrete math review for Foundations of Computer Science. I hope that you found it helpful. In the next section of the course, we will start to take a look at how you might use some of this information to prove things about properties of systems that we are interested in.